All right, hi there, it's Mrs. Pesic, and we are looking at section 3.6, which is called the Fundamental Theorem of Algebra. I know that you have read this section carefully, and so we're just going to go over some highlights and look at a few examples. All right, first of all, the following statements are all equivalent. And before I show you all these statements, let's take this little example guy up here, and we're going to follow along with these statements with this example. So let's say we have some function p of x equaling x squared minus 9. The first statement that's equivalent to the rest is a real number r is a root of the polynomial equation p of x equals 0. So in this case, we know that we could find a solution like 3 is a root of this equation, because p of 3 would be equal to 3 squared minus 9, and that is equal to 0. So a real number r is a root of the polynomial equation, means we could say that 3 is a root of the equation p of x equals 0. All right, what else? We could make the second statement that p of r is equal to 0. All right, so in other words, p of 3 is equal to 0. This statement is equivalent to saying that 3 is a root of p of x equals 0. Those are two equivalent statements. We could also say that r is an x-intercept of the graph of p of x. So stating that, we would say that 3 is an x-intercept of the graph of p of x equaling x squared minus 9. That would be equivalent to stating the other two. So now we have three equivalent statements up here on the board. X minus r is a factor of p of x. It's going to be another equivalent statement. So that would mean x minus 3 is a factor of x squared minus 9. All right, and that one is equivalent to the rest. All of these statements I'm circling are equivalent. And when you divide the rule for p of x by x minus r, the remainder is 0. So in other words, if I divide x squared minus 9, and I want to divide it by x minus 3, I will end up getting a remainder of 0. Well, we could test that with synthetic division. 1, 0, 9, I'm sorry, 1, 0, negative 9, bring down the 3, not there. What am I doing? I don't know. Let's see. We'll bring down the 1, multiply, we get 3, add, we get 3, multiply, we get 9, add, we get 0. So sure enough, the remainder is 0 when we divide. All right, so this divided by this gives a remainder equal to 0. And last equivalent statement is that r is a 0 of p of x. So we could write 3 is a 0 of p of x equaling x squared minus 9. So all of these statements that I have circled are all equivalent statements. So hopefully this is tying up some ideas together. We're connecting the ideas of roots of an equation, zeros of a polynomial, x-intercepts of a graph, factors of a polynomial, and so forth, tying them all together. All right, so let's take a look at this example. Let's write the simplest polynomial function with zeros -2, 2, and 4. So if we want to write the simplest polynomial function, remember that if 2 is a 0, what must be a factor? X plus 2. And if 2 is a 0, what must be a factor? X minus 2. And if 4 is a 0, what must be a factor? X minus 4. So this really would be our polynomial function, but we should put it in standard form, which means we should multiply it out. So if we multiply these two together using FOIL, we would end up getting x squared plus 2x minus 4, which would be x squared minus 4. And then let's say we multiply that by the x minus 4 from right here, again using FOIL, and we would get x cubed for the first terms, minus 4x squared for the outer terms, minus 4x for the inner term, and plus 16 for the last term. So this would be our simplest polynomial function that has zeros -2, +2, and +4. All right, so here's the fundamental theorem of algebra. And again, I know that you've read this. Every polynomial function that has a degree greater than or equal to 1 has at least one zero, where that zero may be a complex number. All right, and the corollary to that, which is even more interesting than the fundamental theorem itself, is that every polynomial function of degree n greater than or equal to 1 has exactly n zeros. So that means that you can write any polynomial function in factored form, but the factors may look like a complex number with an imaginary part to it, or an irrational factor, you know, it's got an irrational number in it, and so forth. All right, but the cool thing is that if it's degree 3, it's going to have exactly 3 zeros. If it's degree 5, it's going to have exactly 5 zeros. But some of those zeros may be repeated, some of those zeros may be irrational, some of those zeros may be imaginary. That is the fundamental theorem of algebra and its corollary. All right. So let's take a look at, I'm kind of skip over this example right here because I think you know how to do these problems. At least I hope so. We spent all day in class going over how to solve problems like this. You know that the steps would be, I'll just highlight the steps. The steps would be to list the possible rational zeros. You know that that means find all of the possible p over q's. All right, I would call that step number 1. All right, step number 2 in solving this would be to look at the graph to see where the x-intercepts are. Okay, step 3 would be to use synthetic division to check whether you have zeros or not. And if you do, if you get zeros the remainder, then you eventually need to get to a quadratic factor to finish solving. All right. Okay. And usually I'm a much better typist than that, whatever the word is. Okay. So let's talk about something else. Recall that the real numbers are a subset of the complex numbers. So a real number a can be thought of as a complex number, namely a plus 0i. So that is a real number, but it's got an imaginary part, but the imaginary part has a 0, so the imaginary part drops out. But when we say that we have complex roots, we mean that we have roots of the form a plus bi where b is not equal to 0. So when we say complex roots, we're really talking about imaginary roots. But complex roots, just like irrational roots, they will come in conjugate pairs. All right. So that leads us to the complex conjugate root theorem. Again, I know that you read this in the section. This basically says if a plus bi is a root, then a minus bi is also going to be a root. So for example, if 2 plus 6i is a root, then 2 minus 6i will also be a root of the equation. So let's take a look at an example. Write the simplest polynomial function with zeros 2 plus I and 1. So what's the simplest polynomial function that has zeros of 2 plus I and 1? Well, just like the example, excuse me, just like the example that we did here, you're given the zeros, so the first thing you want to do is write the factors. All right, So in this example, if one of the zeros is 2 plus I, then we want x minus the quantity 2 plus I to be a factor. All right, and if 1 is a 0, then we need x minus 1 as a factor. But wait, what's that complex conjugate root theorem say? It said that, if 2 plus 6i is a root, then 2 minus 6i is a root. So if 2 plus I is a root, then 2 minus I also has to be a root. So let's write down the corresponding factor for that. So we would have to have x minus this 2 minus I root. So again, if you have 2 plus I is a 0, then 2 minus I has to be a 0. And that means you're going to have two factors, x minus the first one and x minus the second one. And don't forget we also had this 1 as a 0, so we had to write x minus 1. So we need to write the polynomial equation, and we can't just leave it like this. So we're going to have to multiply it out. All right, I would suggest that we distribute the negative. So we would have x minus 2 plus I for this first one, and x minus 2 minus I for this next one. And we're going to multiply those together first, and then we'll multiply by this x minus 1. All right, so to multiply these two, I would recommend the box method. And I would put the x minus 2 plus I across the top, and x minus 2 minus I across the side. And then when we multiply, we get x squared minus 2x, xi, minus 2x plus 4 minus 2I, and negative xi, positive 2I, and a negative I squared. Okay, so maybe some things will subtract off for us, like the xi and the negative xi subtract off, and the negative 2i and the positive 2i subtract off. It looks like I could combine the negative 2x and the negative 2x and get negative 4x. So far I have x squared minus 4x. I've got this 4 and I've got this, so I'll write plus 4, but I also have a minus I squared. Isn't I squared equal to negative 1? So this would really be the opposite of a negative 1. So that's going to be a positive 1. So I really have plus 1. So I get x squared minus 4x plus 5. All right. Now that I have that, that's really just this piece right here. Okay, just multiply those two together and I get x squared minus 4x plus 5 when I multiply those together. So don't forget that we still have to multiply this guy by x minus 1. All right, so for your first notes must do, I'm going to have you finish this up. You are going to multiply the x squared minus 4x plus 5 times the x minus 1. All right, this is our function that we've been asked to find. It is a function that's going to have roots 2 plus I, 1, and of course 2 minus I also. So go ahead, notes must do number 1. And you are going to maybe use a box method or something to multiply these two together. Maybe put x, negative 1, x squared minus 4x, and 5, and so forth. All right, that's notes must do number 1. All right, and let's see. Let's take a look at this example. Write the simplest polynomial function with 0, square root of 3, and negative 2. Again, if square root of 3 is a 0, then x minus a square root of 3 would be a factor. And if negative 2 is a 0, then x plus 2 is going to be a factor. But hold up, this is a complex 0, meaning, it's an irrational 0, meaning that its conjugate is also going to be a 0. So if I was going to list zeros, I could say, yeah, negative 2 is a 0, square root of 3 is a 0, but negative square root of 3 is also going to have to be a 0, which means if negative square root of 3 has to be added to this list, then x plus square root of 3 is going to be a factor. So at this point, our function f of x is going to look like just this. All right, all of this together, that is our function. And I would recommend that you multiply out these two first. If you do FOIL on that, you would get x squared minus square root of 3 times x plus square root of 3 times x and minus square root of 9. All right, that's just for this part. And don't forget, we still need to multiply that by x plus 2. Okay, and then we can see that the minus square root of 3x and plus square root of 3x are going to subtract off. Minus the square root of 9 is really minus 3, right? And so we get x squared minus 3, and you're going to multiply that by x plus 2. All right, so notes must do number 2 is going to be you finishing this one up. Write f of x equaling, and you got to multiply this out. This time you can just use FOIL to get your answer. All right, that's notes must do number 2 is to finish this problem. All right, and last problem is to find the zeros of f of x equaling x to the 4th plus 15x squared minus 16. So for this problem, if we're going to find the zeros, let's follow our procedure. We find the p over q's. We could list them, right? But maybe we should take a look and see if this thing is factorable first. Well, I see that this is an even power, and this power here is half of this first one, and that this is a constant. So that does make it possible that it can be factored by using product sum. So let's try that. The product would be 1 times negative 16. That's a negative 16. And the sum is 15. Are there two numbers that will work? How about 16 and a negative 1? So if we try that, we're going to take out the 15x squared and replace it with a 16x squared and a minus 1x squared. So I get x to the 4th plus 16x squared minus 1x squared minus 16. And if I factor by grouping, I can factor on x squared. I get x squared minus 16 and a minus 1 times x squared minus 16. I'm sorry, something's wrong. X squared plus 16 and factor on negative 1, and this would be x squared plus 16 also. I hope that looks correct. Okay, and then notice that we would factor out the x squared plus 16. And we still have that times x squared minus 1. Hopefully you're all okay with factoring by grouping, because that's what we're doing here. And then really, we're trying to, the directions are to find the zeros of this function. Notice it is a degree 4. So how many zeros should there be? 4. So how are we going to find these? Well, we're going to set each of these equal to 0 and solve. Here, if we set x squared plus 16 equal to 0, subtract 16, we get x squared equaling negative 16. We take the square root of both sides. Don't forget the plus or minus. So we get x equaling plus or minus square root of negative 16. You know how to solve square root of negative 16. That's plus or minus negative 1 times square root of 16. So that's plus or minus I times 4. We'll write that as 4i and negative 4i. And then what about this one? We get x squared minus 1 equals 0. And we add 1 to both sides. We get x squared equaling 1. Take the square root of both sides. Don't forget the plus or minus. And we get x equaling plus or minus square root of 1 is 1. So we needed to find 4 zeros. And our zeros are going to be the 4i, the negative 4i, the 1, and -1. Those would be the 4 zeros for this function, x to the 4th plus 15x squared minus 16. All right, that's it for this video. You will have some homework problems and a GGA next class. And we'll see you next time.